And we're back to wrap up 18-3. Here we're going to take a look at example number 4. Hopefully you've tried this on your own. Let's go ahead and go over that. It says to write the equilibrium expression for the following reaction. It gives us the solubility or the dissolving of aluminum hydroxide. And so our KSP is going to equal the aluminum ion raised to the first power, because there's just a 1 out front, times the hydroxide ion cubed, because there's a 3 out front. And of course, you leave the aluminum hydroxide off because it is a solid. In letter B, it says determine the solubility product constant if you are given the concentrations. So let's go ahead and plug those values in. KSP will equal 4.16 times 10 to the negative 9. We're going to multiply that by 1.25 times 10 to the negative 8, and that value will be cubed. And if you perform that calculation, you get 8.13 times 10 to the negative 33rd. That is an incredibly small number, which means that this is not very soluble. It's if you were to write that out, again, that would have a 0 point with 32 zeros, then the 813, very, very small. This equilibrium lies very, very far to the left. Now, it does say to determine the hydroxide concentration when the aluminum is 4.5 times 10 to the negative 6 molar. So let's go ahead and do that. We have KSP equals the aluminum concentration times the hydroxide concentration cubed. We'll plug in our KSP, 8.13 times 10 to the negative 33rd, equaling 4.5 times 10 to the negative 6, and that will be multiplied by the hydroxide cubed. Divide the 4.56 times 10 to the negative 6 over to the other side. Of course, those terms will divide out. The hydroxide ion concentration cubed will equal 1.81 times 10 to the negative 27. We're not done yet because we are cubing this, so we have to undo that cube by using a cubed root or a 1/3 power. And we'll go ahead and finish the calculation up here. The hydroxide ion concentration will equal 1.22 times 10 to the negative 9, and we are in concentration here, so this will be molar. Alright, so on the test, you should be able to, given the expression, or given the equation, write an equilibrium expression. Given the expression and a couple of concentrations, solve for the K. Given the K in at least a few of the concentrations, you should be able to solve for an unknown concentration. Now, the last topic that we want to cover in this section is what's called the common ion effect. What the common ion effect is, it's a lowering of solubility It's the lowering of the solubility of a salt due to the presence of a common ion. Now, what is a common ion? Well, a common ion is an ion that is found in both salts in a solution. That is the common ion, and I think once we show you these examples, that will be no problem for you to identify. So, scrolling down, the biggest thing here is that you just have to realize this is just an application of Le Chatelier's principle. Le Chatelier's principle predicts which way equilibrium is going to shift when you add or you subtract something from the system. So in this case, down here it says which of the following salts would produce the common ion effect in examples 2, 3, or 4. Well, in reaction number 2, you had silver chloride dissolving, at least to a very small extent, to form silver ions and chloride ions. So anything that will produce silver ions or chloride ions will produce the common eye effect. Why? Because if you add to the product side, anytime you add something, it's going to shift the equilibrium back to the left. And if you shift equilibrium back to the left, that means that less solid can dissolve, more solid would be produced. All right. So which one of these actually produces either silver or chloride? Well, the silver nitrate will produce the silver. Sodium chloride will produce chloride ions, as will potassium chlorides. In this case, this one produces the silver, this one produces the chloride, and this one produces the chloride. So any one of those could produce this common ion effect for silver chloride and not allow as much to dissolve. All right. Give ourselves a little more room here. Let's try this with reaction number 3. Reaction number 3 was lead iodide in equilibrium with the lead ions, they're lead 2+, and the iodide ions. So which one of these will produce or supply either lead or iodide to push this equilibrium back over to the left? Well, the Ki produces the iodides, and the lead nitrate produces the lead. So those would supply the common ions needed to push this equilibrium back to the left. And finally, if we take a look at the last equilibrium we dealt with, which was number 4, aluminum hydroxide forming aluminum ions and hydroxide ions. And so the only one here that will supply either aluminum or hydroxide to push this thing back over to the left is going to be the aluminum nitrate. That would supply the aluminum, which would be the common ion for that particular equilibrium. All right? So in summary, scrolling all the way back up to the original page on this section, we talked about heterogeneous equilibrium, where you simply leave off solids and liquids from the equilibrium expression. This is always true when you're dealing with solubility product constant, because you're always dissolving a solid and forming ions in solution, so you're always going to have to lose the solid there. You should be able to determine KSP. You should be able to write out the equilibrium expression first, then solve for KSP, and then determine an unknown concentration. And we did that in several different examples. And finally, the common ion effect is simply an application of Le Chatelier's principle, where you can cause less of the solid to dissolve by adding an ion that is on the product side, so that it pushes the equilibrium back over to the left and does not allow that solid to dissolve. All right? That concludes 18-3.